So I'm going to be talking about mineral carbonation and hydration processes in peridotite for CO2 capture and storage, but also I've found that it may be that some of the questions that this project is forcing us to ask are more interesting, or the answers are more interesting than the central question that we've been asking, and I'll try and share that view with you as well. So I'm going to give some background, too much. It turns out that I found I actually am interested in and like discussing the societal relevance of this work, and so I'm going to do that. I can't seem to force myself not to. And then I'll give you a brief introduction to the natural mineral carbonation processes in Oman. I'm going to spend quite a bit of time on some new stuff because especially Bjorn and Norm have seen this stuff a few times, so I figured it should be different. So I turned everything upside down. If there's time, then I'll talk about some engineering ideas about accelerating mineral carbonation for CO2 storage and also potentially for geologic CO2 capture. Okay, but before I do that, I guess I interpreted this title and this cover as an indication that we might be putting some emphasis on societally relevant topics, and so I did prepare some material about that, and I just want to briefly start out by talking about global total energy production and about global CO2 in the atmosphere. Okay, so this is the last figure in this great book called Energy at the Crossroads by Václav Smil, and it's logarithmic energy use, global human energy use per year against linear time for the last century, data on the dashed line, and then this exponential fit extrapolated for another 100 years into the future. And it's a pretty daunting figure if you think about it. If indeed this trend were to continue, there would have to be a tenfold increase in human energy supplies within the coming century. And I find that almost inconceivable, but it's also helpful to keep this possibility in mind because it does help you to scale out some noise. For example, we can forget about the debate on whether we've reached peak oil or not. Certainly production is plateauing, and so it just doesn't have any relevance with the question of whether we're going to be able to go up this curve or not. Okay, so what will actually happen and what do people want to happen? Obviously, what will happen, we don't know. It turns out that the doubling time for this particular function is about 30 years. Doubling represents bringing all of the 9 billion people who will be around soon up to the global per capita average energy use. Okay. The last time people in North America had the global per capita average today was in 1750. So it doesn't seem like such an unreasonable prospect to ask to bring the world population up to that level. And you might think, well, we in the Western world can learn a lot about conservation and reduce our use on this kind of plot. 67% conservation doesn't look like much. Okay? It delays the doubling to 2050 by 20 years. So as long as the exponential increase continues, good conservation practices are not going to get us out of this box. The 2050 target would bring all 9 billion people on the planet in 2050 up to the European average per capita use. Okay? Even if everyone in North America drops down to the North American average per capita use. So again, that doesn't seem like such an unreasonable prospect for people to aspire to in the world. Now, you know, before I had seen that figure, I guess I thought that conservation and various things might be a good solution to this problem. And so now I think that we're in kind of a quandary, those of us who are informed about that. And I draw your attention to this absolutely great book. I recently reread it. It's stood the test of time. It's a great book by Kenneth Brower about Freeman Dyson and his son George, who have adopted very different approaches in life. Freeman, as you know, probably was involved in the idea of having a spacecraft powered by nuclear explosions that would travel to the stars, and speeds approaching the speed of light. George was famous in the Pacific Northwest, where I lived for a long time, for designing and building handmade kayaks, and he lived in a tree. So, for a long time, I thought that I would be more like George Dyson, and so we have this peak energy, this is not peak oil, but peak energy concept that he would probably subscribe to, and we're going to slide down this peak energy curve into the kayak, it would be great. Okay, but I think from the perspective of the rest of the world, this actually doesn't look like such a good idea. And specifically, the Green Revolution, which is largely powered by irrigation and use of non-sustainable fresh water supplies, will come to a screeching halt in reverse if we cannot afford the energy to continue to expand irrigation and to make fresh water from seawater. Okay, so it's a prospect that is not good for most people. Okay, so we're left with Freeman, and it's an achievable goal. Incoming solar energy is totally off the scale on this diagram, and fusion is too. So the problem, of course, is not that, but how to get there. So how many of you are old enough to remember Evel Knievel? So here he is on the ramp, right? He's going to jump 16 buses, but he's wondering, if he's going to make it. And but either way, whether you think that you want to slam on the brakes or push down on the accelerator, and you probably should do one or the other. The problem is this. Yeah. And I think to a very large degree, the academic community has forfeited a role in this process, which clearly has a very important geology and geophysics have a very important potential part to play in this. So here's what's happening to fill this gap. This is the tar sands operation in northern Canada, okay, which is currently producing 10% of United States fossil fuel supplies. And it's an amazingly destructive extractive process. They're strip mining it and also doing steam injection to get it out. But it is an economic process, and it will continue. And then we can also take a lot of interest in shale gas, as many people are doing, where again, the knowledge of geomechanics is absolutely essential. And as far as you can tell from what's in the public domain, that hasn't been very applied in a very sophisticated way so far. Okay, so because of the demands for energy and the rather slow build out of alternative energy sources, which in turn are going to have their own resource crunches. For example, every big wind turbine has more than 100 kilograms of light rare earths in it, and that is in short supply, you've probably noticed. So it's quite certain to me that we're going to continue to use fossil fuel at a rate that is likely to be increasing. And indeed, despite a lot of concern about it, atmospheric CO2 emissions have been rising faster than the fastest IPCC prediction in whenever it was they made it. It looks like year 2000, really all converge. While we debate this, the world isn't waiting. So what's happened, though, is that the world response to CO2 emissions has actually slowed down recently. And it's easy to point fingers, but I think part of the problem is that this community doesn't look very afraid. We look like we're surfing on a big wave of grant support. We look like we're benefiting from concern and selling stuff. We don't look like we're willing to make personal sacrifices. We don't look scared. And why? Well, I think because we secretly know that the future is really uncertain. So here I've amplitude matched CO2 concentration in mostly the ice core data, but I added in the atmospheric data here. And global mean temperature variation, where I've done something to the ice core data to sort of bring it into whack with what we think the world does. And you see this nice dance where temperature and CO2 globally have been going together for a long time. But what I want to emphasize is that this pattern has been broken. And the past is not the key to the future. When you actually plot CO2 against global mean temperature variability, where here I've divided the Vostok temperature variability by 2 based on what people think is the relative amplitude of temperature variation in the Antarctic relative to the global variation. And then I plotted the last 150 years here in these field symbols, and in particular the instrumental CO2 record from Mauna Loa in black. And you can see that both of these data sets show a strong correlation between CO2 and temperature. But this global metronome that's been taken away for the entire ice core record is no longer the guide to what will happen. And in fact, most ice core people will not accept the idea that these data have been smoothed by diffusion, or that they've missed century-long events such as the one that's going on now. And so we really are entering a place where we don't have any guide from the past about where we're going. And yet, we're trying to use models that have empirical factors in them that are calibrated on climate variability. Whether we're doing anything better than a linear extrapolation from either this data set or that data set, I have no idea, and I don't know how you would verify to a skeptic that you were getting it right. Whoops, didn't mean to go backwards. Oh yeah, okay, sorry. So, first of all, is dividing by 2 right? Well, nobody thinks that Antarctic temperature variability is 10 times bigger than global temperature variability. So that's not the answer. Here's people's estimates of so-called climate sensitivity to doubling of CO2. They don't look very sensible on this diagram. Will the Earth, is this a kind of a quasi-steady state to which the system will relax? Are we basically doing an instantaneous injection of CO2 in the atmosphere and watching the global climate system relax? It seems like that might be the case, but we still don't really have any idea what the shape of that hysteresis loop will look like. Okay, so why? But what I want you to take away from this is not to go out and embrace the people in Congress in the United States who say, this is all bullshit, so we don't have to do anything about it. I want you to take away the message that we don't have any idea what's going to happen, that we've done something totally unprecedented to the atmosphere. The past will not provide us with a key to what's going to happen, and that there are outcomes that well-meaning, honest people are predicting that look kind of irreversible and might well be fatal. Okay, so once people think they're playing this game, very few people will continue. Okay, so again, while we debate, CO2 goes up. And one possible way of beginning to deal with this is to capture carbon dioxide, for example, from power plant smokestacks, and put it in the subsurface someplace. And a really good starting point for this is to look at the IPCC Special Report on Carbon Dioxide Capture and Storage in 2005. Injection into the sea has many advantages. You can either make the water column into seltzer, which is basically accelerating what will happen anyway, or you can make puddles of dense CO2 fluid on the seafloor where it's denser than water. Both of them have the downside that they lead to fairly extreme local acidification. And for that reason, I guess they're largely off the table now. But all of these things have downsides. And the question is, how worried are we? Another thing that's getting a lot of attention and has a lot of detail in this figure because everybody kind of in this community kind of loves it, is injecting carbon dioxide into subsurface pore space. And this is something that, a lot of the reason for this detail is that this is something that the oil industry knows how to do, has been doing. They're injecting 10 to 20 megatons of CO2 per year for enhanced oil recovery. Okay, and they'd love us to pay them to lose some of that CO2 along the transport path, but they're doing it anyway. And there are several big projects that are really, truly, strictly storage projects, not just enhanced oil recovery involving CO2 injection that are pretty far advanced. So it's not too hard to do a megaton a year into the ground. And finally, and you can tell from this figure that this is kind of a fringe idea, there's this enigmatic blue building here that's labeled mineral carbonation. And it's not at all apparent from the picture what the hell's going on in that building. But what's going on in that building is that people are filling beakers with bits of rock and CO2-rich fluids and reacting them to make solid carbonate minerals. And once you do that, the solid carbonates are stable for thousands or millions of years, as you know, because maybe you would like to protect them from the rain, but we seem to be doing all right with cathedrals in Europe without even protecting them from the rain. So this is a very, very permanent storage mechanism. Based on, these are mostly chemical dissolution rate data, mostly at pH 8 for comparison. We're looking at reaction rate and mass fraction per second, which is temperature for a given grain size. And you see, first of all, plagioclase feldspar, which is probably the most important mineral in the Earth's crust, has a rate that depends fairly strongly on pH. But even at pH 3, plagioclase feldspar dissolution rates are orders of magnitude lower than olivine dissolution rates. And in fact, this filled diamonds, these are experimental full carbonation experiments, not just dissolution experiments. So for whatever reason, with high sodium bicarbonate concentrations, olivine at pH 8 is 2 to 3 orders of magnitude faster than plagioclase at pH 3. And for this reason, people have mostly focused on olivine when they try to come up with schemes for mineral carbonation. Okay, but one of the primary proponents of this is Marco Mazzotti in Zurich. And he's the lead author on the chapter in the IPCC report on mineral carbonation, and he says it's not ready for prime time. Okay, what these guys have in mind is they quarry olivine someplace, bring it to the power plant, grind it up, build a pressure vessel, put the olivine in the pressure vessel, keep the temperature high with a lot of voltage, take CO2 from the power plant, put it in the bottom, and carbonate olivine. And that process, as you might expect, about doubles the energy requirement for a given output from the power plant. So Marco is still working on this. One of his latest ideas, which seems very promising, is to use flue gas rather than CO2 purified from flue gas, because about half the energy cost for this process is the capture. So, but you know, it's not ready to go. So in that blue building, there is a tiny red room inhabited by like about 20 people on this planet who think that it might be a good idea, instead of bringing the rocks to the power plant, to bring the CO2 to the rocks. And you are now unfortunate enough to be stuck in a room with this one member of this fringe group for the next 40 minutes or so. Okay, so we've actually gotten to the point now where we can no longer share all our thoughts in one talk, and I'm trying to force myself not to. So what I'd like to do now is focus on what I think we understand the least well about the natural mineral carbonation process and the potential engineered in situ process, as we call the idea of bringing CO2 to the rocks. Okay, so these, for starters, this is a natural, partially carbonated, hydrated peridotite in Oman. These white things are carbonate veins. You can see, just looking at the picture, that there's a hierarchical fracture system, as we learned from Bjorn Takalit, with a multi-generational deposition and fracture history, and so on. Oh, okay. So there's some things about the mechanics of this process that we don't understand, but we invoke it all the time. Okay? So, for example, hydration above subduction zones is invoked to explain the buoyancy and rheology of the mantle wedge above subduction zones, transport water down the subduction zone in perhaps larger quantities than any other part of the subducting process in hydrated peridotites is invoked to explain intermediate depth earthquakes. We have all these great ideas about the wonderful effects of fully hydrating peridotite, but we don't understand how that works. In fact, there's every reason to think it can't happen.
Have you told your lawyer this?
Okay, so let's go to Oman and see that in fact does happen. So here's a topographic map. Oman is along the Gulf of Oman, across from Iran here, and the Indian Ocean. And these mountains in northern Oman are underlain about 60% by a big chunk of oceanic crust and upper mantle that was thrust onto the continent in the late Cretaceous. Okay, when this happens, everybody here knows what peridotite is, right? Yeah? When this happens, we take this nice protecting blanket off the peridotite. Plate tectonics does us the favor of pushing it toward the surface. Erosion exposes it. This is like a battery. Water and the atmosphere are really, really far from equilibrium with this rock. And there's a huge chemical potential gradient across the interface that the in situ methods seek to use that chemical potential to make the process of mineral carbonation quicker and cheaper. So here's a manifestation of olivine carbonation or mineral carbonation in Oman. In the background here, you see mountains underlain by partially hydrated serpentinized peridotite. And in the foreground, these are pH 12 springs coming out of the peridotite. When they come out, they have no carbon in them at all. All the carbon that was in the recharge fluid has been lost along the reaction path. They come out full of calcium hydroxide, and they combine with atmospheric CO2 on the surface to form these big travertine deposits. If any of you have ever been to Mammoth Hot Springs, this particular deposit is about 4 times bigger than Mammoth Hot Springs, but it's not formed by cooling of water full of solute. It's formed by water coming out at the mean annual temperature in Oman that's reacted with the rocks, and then a similar low temperature reaction with the atmosphere. A much larger volume of carbonate in Oman and the peridotite in Oman is in these little carbonate veins, these little magnesite potato chips in serpentinized peridotite, and they don't look like much, but they're kind of ubiquitous. And so when you add up their abundance in an outcrop and then multiply by the volume of shallow peridotite in Oman, you get a number that's about 10 to 15 times bigger than the volume of the travertines. The process that's involved, okay, is hydration, which I haven't bothered to balance, but you have magnesium silicates combining with water to form serpentine and maybe brucite and maybe magnetite. That process itself is super interesting, and we're really coming to understand that it's a significant source of, potentially anyway, of abiotic hydrocarbons, among other things. So here is an outcrop of serpentinite on the coast of Turkey that has been on fire for the last 2,000 years because of methane evolved from the serpentinization process. And here is a very recent and beautiful paper by Tom McCollum and his colleagues looking at synthesis of alkanes and alkenes in a chemical environment that is produced by serpentinization. So it's really, really interesting, but we're not going to talk about it. So then there are reactions which involve mixed hydration and carbonation. So we can take olivine and react it with a lot of water and a little bit of CO2 to make serpentine and magnesite. We can raise the partial pressure of CO2 and instead make talc and magnesite. Or we can raise the partial pressure of CO2 still more and make magnesite and quartz. So every single magnesium atom is now carbonated, and the resulting silicate is pure quartz. Okay. In order to understand the travertines, we have to confess that there's another component in this that matters. There's calcium in the rocks, not only in these calcium pyroxenes, which are not that abundant, in fact, in Oman, but in gabbro dikes and veins and platinum peroxenate dikes and veins in the peridotite. Reaction with water and CO2 in that system forms serpentine and calcite in equilibrium. In the natural system, that actually happens in 2 steps. It's because there's a kinetic delay in the calcite precipitation. So you have serpentine and the formation of these highly alkaline calcium hydroxide waters, and then they come out on the surface and react with CO2 to form calcium. Okay, and since this great papers by Ivan Barnes and Jim O'Neill in the late 60s, and here embodied in some nice geochemical modeling by an Italian group led by Marini, we understand some of this pretty well. So carbon and magnesium concentrations in these fluids correlate so well that I'm just going to show them to you on one plot together. Rain falls on the peridotite, and surface reaction with the peridotite leads to increasing magnesium concentrations and uptake of CO2 from the atmosphere to balance that. So if you go around and measure standing water, wadi water, well water in Oman, you get these waters that are very rich in magnesium bicarbonate. That then disappears into the ground, and the next thing we see is this alkaline spring water with no magnesium and no carbon in it at all. And we understand that process pretty well as the result of subsurface precipitation of magnesium carbonates plus serpentine. Okay? So in that sense, the subsurface veins that we observe and the travertines are genetically linked. And so, well, just an aside, the storage capacity in peridotite is huge. In Oman alone, there's enough peridotite that if we could carbonate every single magnesium atom, you could take up 33 trillion tons of carbon dioxide, or the entire present-day anthropogenic output for 1,000 years. So the size of the reservoir is not the issue, the rate is the issue. Obviously, or we'd all be dead because there wouldn't be any carbon dioxide in the atmosphere. So here's another one of these travertines. Peridotite in the background. The catchments that we work in are entirely underlain by peridotite, at least on the surface. And you see in these rim flows, you can see these little scums of calcite forming. And so when it rains, those scums get knocked down to the bottoms of the pools, and they form another little lamination on the growing travertine surface. Okay? Within days, there are new scums on the surface. So this was the first indication to me that, as a geologist, something that happens in days is supersonic, right? So that maybe we should look at the rates. And so over the years, we've gathered a pretty large data set of carbon-14 ages on whole rock samples from Oman, and the travertines are generally they're generally carbon-14 datable, less than 50,000 years old. But the surprise to me was that the veins are also, with very few exceptions, carbon-14 datable. They have a mean age of about 26,000 years. So, at first glance, this is hard to understand because obviously the opalite's been sitting around eroding on the surface for a lot longer than 26,000 years or 50,000 years. So what's going on? And we can come up with various hideous open system options that I don't want to discuss except maybe at the end. But the best way that we understand these data is actually kind of a steady state where there's a fairly shallow weathering horizon where this magnesium carbonate veins form, and then that's eroding at the same rate that it propagates downwards. Okay, so we get a rate from Oman of about 1,000 tons of carbon dioxide per cubic kilometer of rock per year. Or it's pretty easy to remember, 1 gram per cubic meter per year. And that's obviously not fast enough to offset the human output of 35 billion tons a year. So we have some ideas based on other people's experimental data about how that might be accelerated. There's an effect of temperature on the carbonation. So this is the carbonation rate relative to the rate at 25 degrees C in air. And so there's a temperature effect, which you can see here. It's Gaussian, or I fit it as Gaussian. And then there's an effect due to increasing the partial pressure of carbon dioxide, which goes as the square root of the partial pressure. And if you combine high partial pressure up above about 75 bars and the temperature of 185 degrees centigrade, you can achieve a million to 10 billion fold enhancement in the rate of olivine carbonation. So if we take that by the present day rate in Oman, we get a gigaton of CO2 uptake per cubic kilometer of rock per year. And when you get that kind of number, that means that you're potentially in the game with something that could make a difference. It doesn't mean that it will happen or anything, but it means that you might want to go forward. The other thing that we see in Oman is an ancient system that is Cretaceous, where these things called lisbonites are 100% carbonated periddotites. They're composed of magnesite plus quartz, plus a little bit of chrome spinel to persuade you that these weird things used to be periddotites. And in fact, a lot of them are very nearly isochemical with the peridotite host, except for CO2 and water. But they're just totally bizarre mythologies with often a magnesite-rich matrix and quartz veins. The lisbonites, interestingly, formed at about somewhere in the range of 150 to 200 degrees centigrade, as best we can tell now. And because they have magnesite plus quartz and not talc in them, we know that they formed at a very high partial pressure CO2. So most likely they formed when the hot peridotite was overriding carbonate-bearing metasediments that's right underneath the base of thrust. And indeed, the lisbonites are almost all within 500 meters of the base of thrust of the ocean. So what's cool about that is that the complete carbonation process happened at pretty much exactly the sweet spot for the olivine carbonation rate. High PCO2, 185 C. Okay, so that's all great. But here's the problem. We don't understand how this could work, and there's every reason to believe that it can't, except for the geological evidence. Why not? Well, one thing is that you can anticipate that the rate should decline over time just because of the exhaustion of the reactants in the rock. Okay, now that's not a terrible. The rate, I'm showing you some experimental data here, and it's not that bad. I mean, I've been using the 1 hour data for what I've been showing you, but it's not that awful. But there are many more awful things. As olivine dissolves, it typically does so incongruently. Magnesium goes into solution relatively fast, and it leaves behind a silica-rich layer that the engineers like to call a passivating layer. We would maybe call it a reaction rim, which over time is going to slow down the reaction process with the fluid because you have to diffuse components through this solid reaction line. And finally, there's just the problem that this process potentially increases the solid volume by a lot. And so when you're precipitating carbonate in the pore space, the permeability could crash. And then it doesn't matter what the reaction rate might be, it just can't supply CO2 to the rocks. So for all these reasons, it's easy to find in textbooks explanations for why this is called retrograde metamorphism in metamorphic petrology. And all textbooks explain that retrograde metamorphism is self-limiting for all of these reasons. Okay, and that it rarely, if ever, goes to completion. So, yeah, here we are again looking at these lisbonites. It's kind of washed out. This is a chrome spinel. This gray material is magnesite, and the bright stuff is quartz. And you see little cracks filled with quartz down to a scale of about 10 microns. So geologically, theoretically, this can't happen. Geologically, we see that it did happen, and we also see that there's this hierarchical crack network that clearly can't have all been sealed at once, and clearly played some role in bringing reacting fluids into the rock. So it turns out that Bill Fife proposed in 1985, and maybe other people before him, I don't know, that there's actually a positive feedback in some conditions for these reactions that increase the solid volume. That the internal compressive stresses, as the solid volume starts to rise, can drive fracture, which in turn maintains or even increases the reactor surface area and permeability. So you actually could get into a positive feedback regime that might even accelerate. And a lot of people here at TGP have spent a lot of time thinking about this. This is a particularly beautiful illustration from a paper by Royn et al. In UPSL in 2008, where they have a block of nominal rock, which is undergoing some kind of hydration or carbonation reaction. And as the volume expansion on the edges of the block of rock drives cracking, that provides faster access for the fluid, which is then in a runaway that eventually consumes the entire volume of the probe. But we really, I would say, don't understand the physical regime in which that does and does not happen. Just to go back and look a little bit at the outcrop scale, you can see here this is a serpentinite that's partially carbonated with little teeny cracks filled with carbonate veins. And then over here, you can see that eventually these cracks got sufficiently close together on the time scale of this process that diffusion filled in the intervening bits. And the rock is 100% carbonated. We can see a similar thing here with this famous kernel structure, where here there's actually carbonate and serpentine in these rocks, and no olivine remaining. You can see that the cracking process went right down to well below the grain scale. Okay, the original olivine grain size is typically millimeters to centimeters. The crack spacing is typically tens of microns. If you took away these alteration products, this wouldn't be a rock; it would be dirt. And so the idea that first the cracks formed and then the fluid came in and did the alteration is just really not a viable one. Here's another example of that kind of thing. And here you can see there's been a lot of volume expansion in this outcrop. These are magnesite veins with chunks of peridotite in them. Clearly, not all the magnesium in these magnesite veins came from these peridotites. It came from somewhere else. And also, clearly, this clast here was not in the air before the magnesite veins formed. So you can see that the volume expansion was accompanied by carbonate formation. That doesn't mean that the carbonate crystallization caused it, but it might. Okay, and again, you look at this listronite photo, which has a cracking scale of 10 microns. Okay, well, it turns out that there's a pretty decent literature on an analogous process going back 60 years, and that is so-called salt weathering. And this particular picture has never been published. You can find it on the website of George Scherer at Princeton. These are blocks of limestone with their feet in water saturated in sodium sulfate salt. And the water climbs up into the blocks by capillary action. Evaporation increases the sodium sulfate concentration until salt starts to crystallize. So even though there's a net loss of fluid mass in this system, there's local compressive stresses due to the forming salt crystals in the pore space that shatters the rock. And because of our appetite for putting salt on the roads and sidewalks, especially in North America, there's a lot of engineering interest in this because it breaks bridges and building foundations and statues. So some people think that some of the driving force comes from surface energy, that small asperities of crystals growing out into the pore throats have high radius of curvature that drives the concentration gradient and leads to crystallization on the big round parts. That's probably not the whole story, but what you do have to believe in this picture is that there is this nanoscale film that allows transport to that growing crystal interface against the rock, even when the compressor stresses get to be hundreds of bars. It's amazing, but it's true. And this has received quite a bit of interest in the physics community, and there's been a number of experimental measurements of the pressures and so on in these functions. So they really do exist. Okay, so people have worked out fairly simple scaling for the overpressure. That is to say, the deviatoric stress due to this process, which is proportional to the log of the concentration in the fluid over the equilibrium concentration, or in a little bit more sophisticated terminology, is proportional to the solubility product. Okay, where you divide the activities of the solutes that combine to form this crystal by the equilibrium constant. So for sodium chloride, Steiger works out overpressures of up to a kilobar. For crystallization with supersaturations of 1.4 times the equilibrium concentration, we can infer that magnesite is a notoriously sluggish to crystallize. Very, very large supersaturations are required, at least in the laboratory. And so potentially, you could derive overpressures that are 10 times larger than those for the sodium chloride system. Okay, so I've showed you this proposed scaling and this one. But for us, we're often working on ancient rocks where we don't have the fluid compositions, and so we can't calculate the solubility products. So it is the case, though, that if we knew the free energy for the crystallization from fluid alone, and I don't mean the dissolution part, that is related to the activity product, and we could then use this kind of proportionality to calculate the overpressure that's at least possible. So if we were in a situation where, in fact, dissolution was rapid compared to crystallization, then the free energy change of that entire reaction would be similar to the free energy change of the crystallization alone, and we would know what the overpressures might be. Here's the free energy surface for the olivine plus water going to serpentine plus brucite reaction. Temperature, pressure, free energy. Here's the equilibrium phase boundary. So of course the driving force for crystallization at the equilibrium boundary is 0. It increases outwards, and it's mostly a function of temperature. So if the temperatures are lower than about 275 degrees centigrade, and the partial pressure of water is more than a couple of hundred bars, then we can expect that there might be sort of maximum possible values for the overpressure might be on the order of 300 MPa, or 3 kilobars for those of you who are as old as me. And indeed, it looks like that sort of stress is achieved. So this is this great paper by Bjorn Jantveit and his colleagues. These are partially serpentinized olivine crystals in a matrix of plagioclase, which is basically not altered. And what you see is that the volume expansion due to hydration of these olivines with these green serpentine veins and cracks in the original crystals, the volume expansion due to that reaction has driven cracking in the host plagioclase. And so, and thanks to Bjorn for inviting me here and for a great meeting. Greg Hirth had been trying to write a paper about his paper. So the strain energy density in that system is probably more or less balanced by the fracture energy density in the, as the resulting fracture energy density in the plagioclase. And so the strain energy density is related to this strain squared. And the fracture energy is related to the surface energy. And then in 2 dimensions, the sum of the lengths of the cracks divided by the area of the crack density. So we can then combine these relationships and derive an expression for the stress in terms of the crack geometry. And it turns out that the sum of the lengths over the area is 1 over the crack spacing in the plagioclase. And so putting that and some well-known constants into this expression and observing that the crack spacing, I was getting ready to measure this and I went back to your paper in this nice histogram. The crack spacing is about 5 microns. We get an overpressure of about 300 MPa, which is, as I say, consistent with the free energy estimate. And, you know, it might even be a stupider way to do this. I'm not really sure. But if we look at the serpentine veinlets, the strain due to the volume expansion is something like the degree of volume expansion where the serpentine exists, times the width of the veins divided by the length of the spacing between the adjacent olivine grains. And again, this gives us a value of about 300 MPa. So it looks like crystallization of plagioclase can lead to overpressures of 3 kilobars, which is sufficient to break most rocks and cause frictional sliding on existing surfaces down to considerable depth, you know, crustal depths. 5 meters. We'll get where we get. So just one more picture here. This is another olivine and plagioclase rock. Probably not all of you can discern. I don't even see the alteration. As an igneous petrologist, this looks beautiful to me. I know exactly. But anyway, if it's for those of you who... So here's the olivine outlined, and you can see these serpentine veins. And what's interesting about this sample is they're kind of anisotropic. I'm not sure why. It's not usual. But now let's forget about the olivine and look at the plagioclase. And what we see is that the crack density in the intervening plagioclases is very strongly related to the width of the plagioclase intercerts between the adjacent olivine crystals. Okay, so this is exactly what you would expect. And we can then derive a simple expression that suggests that the crack spacing should be proportional to 1 over the square of the spacing. So I haven't done this measurement yet, but I will. And now I anticipate that the data are going to look something like this. I'm actually not sure if this is right in 3D. Okay, we can also try and do some thinking about where the rate of change of stress due to this process will be large. So we have these elaborate expressions for the rate of olivine carbonation as a function of CO2 partial pressure and temperature. And we have equally elaborate, although almost unknown, expressions for viscous relaxation of carbonates under these conditions. Although actually, I think I might have seen my first steady state flow law for carbonate under these conditions yesterday. But anyway, so we can anticipate that this rate will be large when the crystallization rate is large. But that it will be a kind of strongly asymmetric function of temperature because the viscosity goes down very rapidly with increasing temperature. So at very low temperatures, the rate of the increase in stress due to crystallization is pretty small, and whatever viscous relaxation things might be able to happen down there might be somewhat important. But it looks to me like that will steadily head towards cracking. Okay, then we go through this big peak. And for olivine carbonation, that's going to be 185 C and more than 70 bars PCO2. And then there's going to be a strongly asymmetric crash of that process at higher temperatures. Changing gears just a little bit, we were fortunate to be visited by a very talented applied mathematician named John Rudge, who, somewhat grudgingly, worked with us on this problem. And we have a fairly fancy bunch of scaling rules about the rate of reaction-driven cracking, making numerous rather large simplifying assumptions. But if we apply that to the process in Oman, we get a rate of about the propagation of a planar cracking front on the order of 10 to the minus 3 to 10 to the minus 4 meters per year. If we increase the temperature, we get an order of magnitude out of that. If we increase the PCO2, we get another order of magnitude out of that. If we have advective flow and cracks, we get several orders of magnitude. And if we push that flow to 1 centimeter per second, then we get propagation rates that are truly prodigious in the order of a kilometer per year. So this doesn't prove anything except that we shouldn't stop working on it yet. Obviously, some of these things are relevant to other cracking problems that are concerning people right now. So, for example, the shale gas people currently do something which works, but is unbelievably crude. They have these things called stratopackers that they drive along the pipe in pairs, and they just drive the pressure up in a little region of a pipe and make a fracture or open up some stuff, and then go on down. And you know, the most they can achieve, really, you know, even with spending a huge amount of money, are crack spacings on the order of meters to 10 meters. So obviously, they would benefit greatly by knowing a process that created a highly ramified crack network that went to much smaller scales. And there's a similar problem for the geothermal power industry in that they don't want big cracks, they don't want short circuits that will mine the heat out of a small mine. They also need to form highly ramified crack networks. And it's possible that the community of us thinking about these things can come up with some ideas that might be helpful. An interesting little sidelight is that it's proposed that the primary porosity in shale gas reservoirs is caused by a process like this, where the maturation of kerogen to form, you know, oil, they call it, involves a volume expansion, decreases the density of the fluid. And somebody long ago calculated the overpressures due to that process on the order of 100 to 1,000 bars. Okay, I will not have time to talk about another aspect of our research that is actually a little bit simpler, but I'd be glad to answer questions about it or provide you with papers on it. The engineered solution, one engineered solution that we've thought about a little bit is to create a higher permeability network in the subsurface mechanically, heat that volume, and add this magical baking soda, which turns out to be a catalyst. And then, because this system is exothermic and self-cracking, in a happy world, you can envision that it's largely self-sustaining without a lot of additional energy input. I don't think we're going to do any of this on an industrial scale in the next 20 years. Doing 1/10 of the human output by moving CO2 around involves moving as much fluid as the oil industry moves every year on the surface of the planet. It involves a build-out of something that looks like the oil transportation network just to take out the garbage. And I don't think that people are worried enough to do that. And I can see that it's very likely that we're going to be increasingly distracted by some other issues. Yeah. So it may turn out, though, that in a generation or so, people get to find out what it's like to have 600 ppm CO2 in the atmosphere, and they might not like it. And then the process of dialing that down again is much more difficult than what I've described to you so far, because the concentration in the atmosphere is 100 times lower than the concentration of flue gas. Right? Yeah. So it's a thermodynamic problem that is significantly more difficult. But one thing that we might be able to do is really, really dumb. And that is look for places where the geotherm is relatively steep, or get good enough at drilling that going down a few kilometers is not that expensive. And drill and frack, and then ask thermal convection to carry seawater through this network. Now I showed you that reaction of water with peridotite takes out all the CO2. And so if you return that depleted water to the surface, it will draw down CO2 from the air, and that happens on time scale about a year. So this is an air capture system that doesn't cost very much. 3 more slides. It's working. Okay? So, like the system in Oman, there are submarine hydrothermal systems where water is going into peridotite exposed on the seafloor, reacting in the subsurface, and coming back, depleted in magnesium, depleted in carbonate, and doing a secondary carbonate precipitation process on the seafloor by taking up more CO2 from seawater. The other thing to keep in mind is that the geochronological data from Oman and from here show us that these systems can remain active for 50 to 100,000 years or more. They don't seal up, and they don't run out of reactants. So, in this happy little world, the rocks are already hot. We probably don't have to bother with sodium bicarbonate. We don't. We don't pay for CO2 capture. We don't pay for CO2 transport. We don't pay for cracking if we're happy. And it's slow, and it helps to have a decent geothermal heat source. And in fact, so here's a situation where you could do this. You don't want to be spudding in the ocean. It's very expensive. You want to drill on shore and then go out underneath the shallow ocean. This is in Oman, where you see peridotite dipping offshore underneath this cap rock. It's pretty easy to draw these fanciful pictures. And in fact, they look a lot like geothermal power plants in the sense that you want to create this porous network and you want to capture a lot of that water. There's a lot of reasons why you want to capture it, but one is you really would have to mine this low-grade heat. You don't want to solve the global warming problem by heating up vast amounts of sea level. And so even if power generation from this low-grade return flow, low-grade heat in the return flow wasn't economic on its own, you've built this network to get rid of CO2. The power is on the top. Okay, and again, there's many ways to apply this. Thank you very much.